Hey there, awesome physics students. I'm sure you've dealt with batteries before. This is a 1.5 volt battery. Or you've plugged things into the wall and noticed that the wall is rated at 110 or 120 volts. Or you've plugged in your phone to charge it and you've noticed your phone charger outputs 5 volts to charge your phone. Or your laptop charger outputs 19.5 volts. So what is this voltage about anyway? Well, volts our voltage is just the potential energy per charge. That is, it's the amount of potential energy an individual charge has divided by that individual charge in coulombs. So this is going to have units of joules per coulomb. And interestingly, the unit of joules per coulomb can be simplified as volts. So it's a bit awkward in some sense because the thing we're calling voltage has units of volts. It's almost like something have force having units of forces. It's a little awkward, but anyway, roll with it. Mostly we're interested in voltage differences between one side of the battery and the other side of the battery. Or we're thinking about the prongs of the plug that you plug into the wall, and we're thinking about the voltage difference between one side and the other side. And so we're mostly concerned with voltage differences, so we're mostly concerned with potential energy differences. Now, I keep talking about voltage here, but my title up here is electric potential. For our purposes right now, we're going to treat those as the same thing. Voltage is electric potential. That's not quite true, but since we're just learning about it, we're going to treat it as if it is true. Okay, so what actually moves in this battery from one side to the other? It's electrons, and electrons have a charge, a fundamental charge, and that value of that fundamental charge is 1.6 times 10 to the minus 19 coulombs. Now, electrons are negative, and so we say the charge of an electron is negative E, where E is this positive number, and this is called the fundamental charge, or the fundamental unit of charge. Protons have the same magnitude of charge, but it's positive. So if you have one electron and one proton together, the total charge there is 0. Okay, so if I take one electron and I send it from one side of the 1.5 volt battery to the other, what's the energy difference there? Well, the energy difference I can compute. That's the potential energy difference. And by the way, whenever you say potential in an electric context, the implication is electric potential or voltage, not in volts or in joules per coulomb. If I intend energy, then you say potential energy, or you use the word energy. And here I'm asking about the energy difference. And that is going to be, well, you can see I could get the potential energy just by multiplying both sides by the charge. So that's going to be the voltage difference times the charge. And so if I do this for an electron with a 1.5 volt battery, 1.6 times 10 to the minus 19 coulombs. If I do this calculation, I get 2.4 times 10 to the minus 19 joules. Okay, that's interesting, but these numbers are going to be incredibly tiny. So this is actually not always the most useful unit. Oftentimes, because electrons are the ones that are moving so often, we often don't simplify this part and we just leave it as E. And so we say the potential energy difference is just 1.5 electron volts. And the E, this number here is right there. So this is telling you what's the voltage difference that one electron feels. Okay, and it's 1.5 volts is felt by one electron. Let's ask a slightly different question. If we have a proton and an electron, which is, by the way, the simplest atom you can have, right? This is a hydrogen atom. How much energy is stored in this electrically? Or in other words, how much energy does it take to rip these two apart? And in order to rip these two apart, it turns out it's going to take 13.6 electron volts. Now, if I wrote it like this in joules, it would be this incredibly insanely tiny number because we're just ripping apart one hydrogen atom. But given this way, this makes a little bit more sense and is a little more perhaps intuitive. Okay, let's think about one other scenario here. if we think of charge, two charged plates, and let's say they have a voltage difference of 3 volts from one plate to the other plate, how much energy how much kinetic energy does this thing gain if I have a 2 coulomb charge, positive charge, that's traveling from one side to the other side? Well, I can simply use this expression here to convert potential energy into kinetic energy, right? So I want to say, I know that energy is conserved. Conceptually here, what's happening is that potential energy is converted into kinetic energy. The potential energy is just the voltage difference. That's 3 volts times the charge, which is 2 coulombs, and that's converted into kinetic energy, and the kinetic energy is 1/2 mv squared. This is a really nice approach to this kind of problem because I don't have to think, I could have done this before when I thought about electric fields. Electric field points down, therefore the force on this points down, and then I could use the force to compute the acceleration, and then I could use the acceleration to compute the velocity, and so on and so forth. And here I can skip all of that and I can just think about energy. And so you can see that voltages are closely related to energy conservation. Now, to solve this, I'd need to know the mass. But I'm going to argue here that actually this is perhaps less meaningful than some other quantities here. Not always, but sometimes. For example, your electric company charges your electric bill for energy use. They don't charge you for force or velocity. They charge you for energy. And so we can just get the energy of this and just take that as a meaningful number itself. So if I take 3 volts times 2 coulombs, that's going to be 6 joules of energy that is converted into kinetic energy. Okay. Now, one more thing I want to point out here, and that is that remember when we talked about force and electric field and force are best friends. They have to point in the same direction. The electric field tells you about the force. Here, the situation is a little different. The potential energy difference is just the charge times the voltage difference. And so voltage and potential energy are best friends, just the same way that force and electric field are best friends, right? Potential energy or voltage tells you about the potential energy of the charge configuration or the energy that you can extract, just like electric field tells you about the force on a charge, okay?